Exercise 39. Let's talk about the QR factorization of a matrix. So this is from linear algebra. This is an exercise. Show that any m by n matrix A with linearly independent columns can be written in the form A equals Q matrix multiplication with R, where Q is A is matrix n by n. So this would be again n by n. This would be n by n. N by n matrix. It's also normal columns. In particular, which means all the column vectors are non-zero and they're orthogonal, and each is a unit vector. R is an upper triangular matrix. Upper triangular matrix with positive. So upper triangular, let's say invertible matrix. Upper triangular invertible matrix. So it's invertible and upper triangular. So because it's n by n, it's just a square matrix, we can talk about invertible. It's invertible if and only if its determinant is non-zero, and as upper triangular, the determinant would be the multiplication of all the entries on the main diagonal, and so the main diagonal would be non-zero, but we require more than that. We require it has positive entries on the main diagonal, or the diagonal is the same. So such factorization actually it has a name which is called QR factorization. So solution, this is a constructive proof. What we do is write A in the form of its columns, A1, A2, AN. So this is n by n matrix, so each one is n by 1 column vector. What we do is with the Grashmeet procedure or algorithm, we got it to A1 tilde, A2 tilde, AN tilde, so they are orthogonal to each other, which means secondly they have the same span, right? That's what we got by Grashmeet procedure. Which means both equal to the column space of A. But we don't stop here. We go to one more step. We do this normalization. And we got u1, u2, un, we call this new matrix, putting this u1, u2, un as column vectors. We call this matrix u. So actually this u will be our q. This is also normal basis, has also normal columns. Okay. Question is why this works. This works mean that I'm going to also define what is R, then this Q and R satisfy the condition. So obviously Q satisfies the first condition with also normal columns. Well, let's construct R to be Q transpose multiplication with A. We claim this R is arbitriangular, positive in tree. So let's see how it happens. So what I'm going to do, I'm going to write this AI into the form of linear combination of UI. So basically UI is in the span of U1, U2 until UI, right? By our construction. The Gram-Schmidt procedure tells you that. For any I in this from 1 to n. So U1 is just normalization of A1. U2 would be give you the same. So U1, U2 give you the same span as A1, A2. And they're orthogonal to U1, right? So in particular, AI is always here in the span with this UI. Let's write it precisely. Let's say A1 equals R11 U1 plus R everywhere else 0. A2 equals R21 U1 plus R12 U1 plus R22 U2 R13 U1 R23 U2 R33 U3, etc. And so you could read that I'm writing AK or AI equals R1K U1 plus R2K U2 plus until R KK UK. And then what is R? R is QT times A. So U1T, U2T, UNT times A. U1, U2, AN. If you do the multiplication, first row, first column, U1 dot product A1, first row, second column, U1 dot product is A2. Similarly, second row, first column, U2 dot product is 1, etc. So basically what you got is this IJ's column become UI dot product AJ for IJ, right? And so what it is, use this expression of AI dot product with U, and with the fact that UI also normal, then U, obviously you see this is actually U1 dot product A1 is R11, U2 dot product A1 is 0, U1 dot product with A2 is R12. U2 dot product with A2 is R22, and then 0 everywhere. So this is our R, which is upper triangular. And the reason all those of the main diagonal are positive is because actually it could be negative, but if it's negative, then we turn this ui into minus ui, and then this will become positive, which means there exists some orthonormal basis such that it's positive. Okay. And now final thing to check is that x equals QR, a equals. So the only question left, a equals QR, right? But notice that what is QR? So a is a1, a2, n. Well, QR is Q is u1, u2, un. R is r11, 0, 0, r12, r22, 0. Rn, r1n, and so when you do the multiplication, it gives you exactly first row, first column gives you r11 u1, which is a1. First row, second column, r12 u2, r22 u2, give you a2. Finally, give you an. And so a equals QR. Let's finish the proof.